Good morning, Earth Science, and welcome back. Today we're going to talk about Chapter 23, which is about the ocean floor. We've talked a lot about the different zones of the ocean and life that can be found there, and today we're going to focus on what we know about the bottom of the ocean. So the first thing we're going to talk about is echo sounding. And echo sounding is originally what we did is to find how deep the ocean was, we would have to take a length of rope and tie it to a line and tie a big heavy weight to the end of it and throw it down. And in the really, really deep ocean, it could take a whole day to do one single depth, let that thing fall all the way to the bottom, record how deep it was, and then pull it all the way back up. What really started to speed up this process is we started to get the ability to use echo sounding, where we used sonar to find the distance to the ocean floor, where we took sound and bounced it off the ocean floor, and then measured the time it took to come back to the boat. Sound moves a lot quicker than rope, or weight does in the water, so it is able to do this process much quicker. We did get better and better at sounding. Originally, we could send just a single beam down in that first kind of picture there on the left, and it wasn't a very speedy process. But now we can send multi-beam echoes, and that cover twice the distance, and it takes us half the time to do the same amount of area. We also got the ability to not have to stop the boat when we were using sonar, so we could, as we were moving, use that sonar to create these maps quicker. The intensity of that reflected sound, we can use it to figure out not only how far the ocean is down, but kind of what it's made out of. We can know if it's a harder material or a softer material. Things like rock and gravel reflect sound waves a lot more strongly than things like mud do. We also, in the ocean, take lots of sediment samples to get an idea of what's down there. So this kind of data gives us a lot of things on climate change, early oxygen levels, uh, life forms, all that kind of stuff. We use this thing called core sampling, where we take a hollow instrument and we drop it down there and it removes one of these cores here that this picture shows. And what the nice thing about this is it preserves layers better than dredging would. Dredging is where you just like scoop up a whole bunch of the bottom and then analyze it. The problem with dredging is in an aqueous environment like water, things get waterborne and they get all muddied up and they don't get nicely preserved. But these cores, as you can see here, are nicely preserved and they usually don't mess up things around them. Now, we've gone even further and we've started to use satellites to make observations on the ocean. Even with the advancements in echo sounding, it's still slow, and we still have done very little of the ocean floor with echo sounding. So to find things in the ocean, we had to sail over it, and we didn't know where they were, so it was kind of at random. That's why it took us so long to find the Titanic. While satellites can't bounce these signals to the ocean floor, we can use them to hit the surface of the ocean. And what we find out is the ocean is slightly higher over undersea mountains and slightly lower over undersea trenches. These satellites are able to take this really small difference, centimeters or lower, and it produces high resolution images of the ocean floor based on those different differences in the height. So a map here taken by a satellite would look something like this. In this map, all the land is black. The dark blue areas of the ocean are the deepest, and then the red areas are the shallowest. So you can see right around here, the Bering Strait's really shallow. You get all these areas around continents that are really shallow. So it kind of gives you a picture of where the deeper ocean is. And you can see these mid-ocean ridges. You can see lots of cool features on here. The next thing we're going to talk about is continental margins. We talked about them before, but we're going to go over them again, looking at the water side of it. This is the underwater part here of a continental crust. So the continental shelf, this is the part of the continent that extends from the floor line to the continental slope. It's usually very flat and wide. And then you have the continental slope here, where your depth increases rapidly, you get lots of sediments accumulation, and these sediments can tumble down deeper into the continental rise. This is on the ocean crust, and it descends from the continental slope here down into the ocean basin or the abyssal plain. So it's kind of that last connecting piece. So it goes flat, steep, kind of flatter, and then the bottom. There are two types of continental margins. The first is active. This is where you're currently getting an ocean plate that's getting subducted here. In this one, the continental shelf is very narrow here. The continental slope is very steep. And then it continues down into a deep ocean trench here. So examples of plates that are doing this are the Nazca Plate, which is in the Peru-Chile area, and then the Pacific Ocean itself is doing this. These active margins can happen at transform boundaries. And when they do, you get a lot of earthquakes that are happening at this boundary between the two of them. The second type is passive continental margins, and these are all on one plate. They are not at a plate boundary. So because of this, there's no ocean trenches, there's no rugged coastal mountains. There's this very broad continental shelf here, very wide continental shelf. An example of this is the east coast of the North American plate, where we have this very it is all one crust here. Our next topic is submarine canyons. These are larger than the Grand Canyon. They slice through the continental shelf all the way down to the sea floor, and there's two ways that they form. They're either from old rivers, such as like Hudson Canyon, which we think it was formed before the ice ages, when sea level was 100 feet lower. As these rivers cut deep channels, they got covered up as the ocean rose, and this channel was left in there. And the second are turbidity currents, where we have great landslides of mud and sand that speed down continental slopes and create these things. And they can be triggered by either earthquakes or gravity. The third part of this chapter is about the ocean basin or the abyssal plain. It's the flattest of all their surfaces. It's covered in lots of sediments from these turbidity currents from land, where we're getting lots of river runoff. They can be up to half a mile thick, and many of these are leftover deposits from the ice ages, when all the continents got scraped by big glaciers and all of the good rock that got scraped off got pushed into the ocean. In the abyssal plain, we'll have things called Abyssal Hills. These are small rolling hills that occur in groups next to oceanic ridges. They raise usually no more than several hundred feet off the ocean floor, but these are the original seafloor surface, and as they've been pushed, they kind of form a little mound, and then there's a flat spot as you get a new push, and then a little mound, and then a flat spot as you get another push, and so on and so forth. As this lava is spewing out of there and making this new valley. All right, deep sea trenches. These are long, narrow, steep-sided troughs that run parallel to continental margins or to volcanic islands. Both on them you have island arcs, where you have chains of volcanic activity. These happen at subduction areas, subduction zones, and because there are these two plates coming together, they're common sites of both earthquakes and volcanic activity there. Now, there's two kind of differences here on continental versus oceanic trenches. When an ocean plate is subducted by a continental one, you get a marginal trench that forms, and volcanic activity happens on the actual continental plate. Versus this is like the Andes Mountains, where we have volcanism on the continent. When an oceanic plate is subducted by an oceanic plate, however, you get a deep, deep trench, and you get volcanic islands form on the top oceanic plate. And Japan here, this is an example of two plates coming together. This is the top plate. This over here is the bottom plate. As it's getting subducted down there, it's both forming this deep trench and forming these volcanic island chains. On mid-ocean ridges, you get really big underwater mountain ranges from these. These can go from a long distance. They currently form a chain that wraps around the world and crosses every ocean. But these things are usually less than 1,000 miles wide and usually around 2,500 feet above the seafloor. We get these at divergent plate boundaries, which is where we get the majority of our new seafloor creation. They're not seamless. They're made of hundreds of little transform faults where these continents have broken up a little bit. Yet we don't get a lot of earthquakes from this area because this rock is still soft and cooling. Seamounts are these cone-shaped mountain peaks that rise above the ocean floor. They're usually found in clusters. They are volcanic in origin. The Hawaiian Islands are examples of seamounts. And this structure is most commonly found in the Pacific, where there's lots of volcanism going on. Geos, these are flat-top seamounts. And what happens is as these guys get above sea level, the tops are worn down and kind of eroded. As they sink on this oceanic crust, they're brought back underwater, and they can sink down to about a mile deep under the surface. So they started at the surface, and they were above the waves. That's what flattened them out, and then they sunk back down and are kind of stuck there. All right, coral and coral atolls. These are ring-shaped coral islands here. How they form is at one point in time there was a volcano, that island that was sticking out through here. As the crust below this island sunk, the corals continue to make new and new layers as they're sinking down. But what ends up happening is the coral ends up at the surface still, and the volcanic island is gone. So you end up with this little lagoon, this blue lagoon here, where it's kind of trapped inside of the coral. These usually have some very unique life forms, bacteria, etc., that aren't found commonly anywhere else. All right, the last part of this chapter is about ocean floor sediments. There are 4 main classes of ocean floor sediments. They're based on their size and composition. We have sand, which is made of large particles, and clays and muds, which are made of finer particles. And then at the bottom of the chain here, we have oozes, like this one here, that are found from, made from microscopic shells. This is an image that is blown up several times, 40 times, 100 times, to see these little guys. We get what's called Terrigenous sediments, and these are sediments that originally come from continental rocks and minerals that get there by erosion and weathering. And these are fragments that get carried by rivers to the ocean. The large chunks of these usually don't make it very far, and the smaller chunks can be carried in the current. So for these guys to accumulate, it usually takes a couple hundred years to get enough stuff to accumulate. This is kind of a picture of some ice here with some Terrigenous sediments in it. As that ice melts, those sediments will fall into the water and start to accumulate down there. The next sediment type is Biogenous sediments, and these come from living sources. They are oozes that are composed of marine shells and skeletons there. They're common in areas below surface waters with high protist and animal concentrations. We have 2 types, and the first is Siliceous Oozes, which contain at least 30% calcium carbonate, that's CaCO3. They're the more common of the biogenous sediments, and half of the ocean sediment overall. They begin to dissolve when you get a lot of pressure added, usually completely dissolving around 4,500 meters in depth. These kind of red areas are where we have these sediments kind of accumulating around the world. The next type here is Siliceous Oozes, and they contain silicon dioxide, SiO2. Here's a picture of one blown way up on a microscope. They're formed from smaller organisms. So these tend to typically drift, these sediments, instead of forming oozes. They're common near the equator and around Antarctica. And both in the deep sea area, both calcareous and siliceous oozes, they accumulate really fast, up to 10 times faster than your Terrigenous sediments down there. So you're getting a lot more of these life-formed sediments than you are from continental erosion. All right, hydrogenous sediments. These form when chemical reactions cause minerals to crystallize from seawater. This picture shows a whole bunch of manganese nodules on the ocean floor there. These guys contain both manganese and iron, and they occur in lakes and oceans where other sediment accumulation is low. So They are kind of just these chemical reactions pulling this out of this water and forming these solid nodules. They can contain cobalt, which is an element that we use to refine petroleum. So, the reason that we study sediments and the importance of it is by studying these, we can determine where old polar ice sheets were formed, get a record of the history of the sea floor, of its water temperature, of its oxygen content. We can see behaviors of prevailing winds in the past. We can see patterns of change in Earth's climate, and we can find both magnetic records of, where the Earth was kind of pointing at the time, and this is what this kind of graph is. It shows the different fluctuations in magnetic in the kind of sediments there. And we also have discovered lots of small extinct species in these sediments that are no longer alive today, or no longer, we haven't found them living today. This is the conclusion to chapter 23. I hope you learned something, and we'll see you in the next one.